Hi there, this is Astrophysics, and this is Telescopes Lesson 1. And we're going to do refracting telescopes and angular magnification. So first of all, the refracting telescope. So a refracting telescope consists of two converging lenses. And light is collected by a wide, long, focal length objective lens, which is f0. That's the focal length of the objective lens. And the image formed by this lens is viewed through and further magnified by a short focal length eyepiece lens, which is FE. And when in normal adjustment, the distance between the two lenses, the one on the left and the one on the right, is equal to the sum of their focal lengths, f0 plus FE. Remember to pause at any point if you want to make any notes. So what we're going to look at next is the ray diagram for a refracting telescope in normal adjustment. So you've just got to learn this, and then when you do your exam questions, it'll literally just say, sketch this ray diagram. So you need an objective lens and an eyepiece lens. Then you draw that. So parallel light from the top of a very distant object. As it passes through the objective lens, the ray at the top will refract slightly, and the one that goes through the optical centre will remain undeviated. And they cross below f0 plus FE. Well, f0 and FE. So you get an inverted real image formed by the objective lens. That's not come up very well, but there should just be an arrow that points down that touches the rays of light. Then you need to do a construction line, which is parallel to the principal axis. The principal axis being the dashed line. So you get a construction line in there, and then refract that through FE. And then use a ruler, obviously, to draw parallel light viewed by the observer, parallel to the construction line. Then dash lines coming off the two lines that you've just drawn in, and you get a final inverted virtual image formed at infinity. So my advice is just to sketch it out, do it again, and just keep doing it until you can remember it. It's the best way to do it. Alright, let's move on. So, angular magnification. So a telescope makes a distant object appear to be bigger by making the image subtend a greater angle, which beta, to the eye than the angle alpha subtended by the object to the unaided eye. So this diagram will help with this. So distant object, so that's the eye. And the virtual image that's produced is obviously much larger. So the human eye is always alpha, and the virtual image produced by the telescope is beta. And the ratio of these angles, beta divided by alpha, is called the angular magnification or magnifying power. So magnifying power of a telescope in normal adjustment. So the magnification is the angle subtended by the final image at infinity to the observer, divided by the angle subtended by the distant object to the unaided eye. So quite simply, that's magnification is beta divided by alpha. So beta is the telescope, alpha is the human eye. And also, if angles are small, so less than 10 degrees, magnification is also equal to the focal length of the objective divided by the focal length of the eyepiece. So magnification is FO divided by FE. So if you want to get that written down, and then we'll do a couple of practice questions. Alright, so here's question 1. So if you want to pause and attempt this one, and then I'll take you through the answers. So question 1, a refracting telescope in normal adjustment of objective focal length 70 centimeters, eyepiece focal length 2 centimeters, is used to observe the moon, which subtends an angle of 0.53 degrees to the naked eye. That's important. So part A, the distance between the lenses. So the distance between the lenses is simply f0 plus fe. So that's 70 plus 2, which is 72 centimeters. Part B, the magnifying power of the telescope. So the equation for magnification is FO over FE, objective lens over eyepiece lens. So that's equal to 70 centimeters divided by 2 centimeters. So that gives us a magnification for this telescope of 35 times. You could put that into meters, but obviously just get the same answer. So part C, the angular size of the moon when viewed through the telescope. So magnification is beta divided by alpha. We need to rearrange to find beta, because we've got alpha, which is the angle subtended by the naked eye, which is 0.53 degrees. So beta is equal to magnification times alpha. So magnification is 35 times 0.53 degrees. So that gives us an angle of 18.6 degrees. And it asks us why the previous answer to part C might be inaccurate. And if you remember on one of the previous slides, I told you that these equations work very well if angles are less than 10 degrees. And this angle is greater, therefore it won't be accurate. Alright, let's move on to question 2. Alright, so if you want to pause and have a go at this one, then I'll take you through the answer. So, a refracting telescope in normal adjustment of objective focal length, so the objective focal length is 120 centimeters, is used to observe Mars. Through the telescope, Mars subtends an angle of 0.4 degrees, so that'll be angle beta. If the magnifying power of the telescope is 160 times, calculate the angular size of Mars to the naked eye. So magnification is equal to alpha, well, it'll help if I know equation. Beta divided by alpha, sorry. And what we're going to do is rearrange to find alpha. So alpha is equal to beta divided by the magnification. So that's going to be 0.4 degrees through the telescope divided by 160, which is the magnification. So to the naked eye, alpha, the angle would be 0.0025 degrees. And then we've got the focal length of the eyepiece lens. So magnification is equal to FO over FE. And we want to find FE. So therefore FE is equal to FO divided by the magnification. So objective focal length is 120 centimeters divided by magnification 160. So the eyepiece focal length, FE, is going to be equal to 0.75 centimeters. Hopefully that one went okay, pretty straightforward. Right, so one last thing for this lesson, chromatic aberration. So blue light is refracted more than red light. You should know that anyway from doing optics. So for a given lens, the focal length is therefore longer for red light than blue. So blue bends best, so blue will refract more, and the red image and the blue image will display in different regions. So it looks like this. So this defect can cause a white object to produce an image with coloured tinges. And this defect is called chromatic aberration, and is particularly noticeable with light that has passed through the edges of a lens. Alright, hopefully you found that useful. Thanks for watching.